exact same principles are going to apply, right? Remember those 3 rules of working with time value of money problems? Can anyone yell those back at me? The first one was you can only
compare the same year. You have to break it down to the same year. You can't look at the future value. You have to bring it down to the present if you're looking at the present stuff. I don't know how I'm explaining that. But
yeah. No, that's exactly right. Yeah, you got to put the cash flows in the same time period, right? You can only compare or combine cash flows that happen in the same time period, right? And if you got moving around, the next 2 rules are if you move into the future, you compound, and the third rule is if you need to move into the past, you got to go backwards. Right? Those are the 3 rules. Those are going to apply with Chapter 4, but it gets a little sticky because we've got cash flows all over the timeline now. We've got to deal with moving multiple cash flows around. And there's some shortcuts that pop out of that when we have specific types of cash flows. All right, so let's look at Chapter 4. Again, we're still looking at time value of money. But now we're going to look at multiple cash flows. All right, and what we're going to do is just look at like 4 different types of basic cash flow structures that most things we're going to run into fall under. All right, we'll define them and then we'll start playing with them to see how they work. All right, the first one we're going to look at different types of cash flows. The first one we're going to look at is called perpetuity. Really fun name, really simple concept. So who read? What is a perpetuity?
Put $100,000 in, and you get that interest every year forever if you never withdraw it.
If you never withdraw the original principal, right? Yeah. So that's exactly right. It's a cash flow stream that happens in equal intervals, and it lasts forever. It goes on forever, it never stops. All right. So let's define this thing first. Let's use the book's definition: a stream of equal cash flows. That occur at regular intervals. And last forever. And you're probably thinking the same thing I did when I first heard about perpetuities. That sounds like something some bookworm academics at his office come up with. That doesn't exist, right? What throws on cash flows forever? Well, these guys exist in the real world. The U.S. government has borrowed in this manner. They've had perpetuity bonds. They don't sell them anymore. The British government still has perpetuities outstanding. They're called consols. And what you would do is pay a set amount. They used them a lot to finance like World War I, World War II stuff. You would pay the British government £100, and they would, for the rest of the time the British government is in existence, pay 10 pounds per quarter for as long as the government's in existence, right? Which we assume will be forever, at least effectively for us, right? They'll be around longer than we are. So these things do exist, and you're actually a little closer to them than you might imagine. Many of your professors' salaries are actually set up as perpetuities, right? So if you've got a chair position or a named chair position, normally the way that's funded is they dump something like $2 or $3 million into a bank account, and then every month they just draw the interest off of that and pay the professor's salary with it. Right? And they leave the principal alone, so that $2 or $3 million sits there, and they just draw down the interest to make those monthly payments into that account, and that's how that professor gets paid. Right, so these guys do exist. It's not just an academic exercise, and they turn out to be so simple. All we can really do with these guys is talk about present value or the rate of return. Talking about the future value of a perpetuity, it's a cash flow stream that never ends. So what's the terminal value? When does it stop? It never does. It goes on forever. So really, we just talk about both the present value and then the rate of return on these guys. Well, let's look at, you guys are like me, a picture really helps. Let's look at how we can create one of these perpetuities and see just how simple it is to price. All right, so perpetuity is a stream of equal cash flows, occur at regular intervals, and last forever. If we were going to map it out on a timeline, it would look something like this. Time period 0 right here, note it has nothing there. Okay, and this is going to be important for the way the formula works, right? There's no cash flow there. But one period later, this thing is going to throw off cash flow C. So one period after 0. And then the next period after that, cash flow C again. Next period after that, cash flow C again. And that's a positive C. So it's throwing off some positive cash flow every period at a regular interval. And then it goes on forever. So the dot, dot, dot means it lasts forever. That first payment doesn't happen immediately. All right, if we wanted to calculate the present value of this thing, right, we know how to do that when we look at each payment as a lump sum. So we take that first cash flow that happens 1 year from now and discount it 1 period, right? It's divided by 1 plus R to the 1. We add that to the present value of the next period's cash flow, and it's discounted back 2 years. It happens 2 years later. The third one is 3 years later, right? And that just goes on forever. So cash flow streams last forever. You probably would wonder, well, the present value is infinite, right? The cash flows are infinite. Well, it turns out it's not. Once we go far enough out, remember these denominators are increasing exponentially. Once you get out 50, 60 years, the present value of those later cash flows is essentially 0. It's like 0.00013, something like that. If you got a $100 cash flow, it's tiny. All right, so eventually they go to 0, and in fact, we can show this a little bit easier. Right? Let's look at creating our own perpetuity. Right? Let's say that we can invest $100 in a bank that pays 5% interest per year, and we can lock in that interest rate now by contract. In reality, the interest rate would vary, but for simplicity's sake, let's just say it's 5%. So when you deposit that $100 into the bank account, at the end of the year, you'll have $105. Right? What you're going to do is draw off that $5 in interest, leave the $100 there to earn interest for another period, draw off the $5 again, leave the $100 there. Right? So your timeline ends up looking something like this. Time period 0, this is when you deposit the $100. Right? It goes into the bank. You let that earn interest over the first year at 5%. So you end up with 105. And ignore the way this timeline is written, it's just confusing. What you do is draw off this $5 right here. Right? So you put that $5 in your pocket. You reinvest this $100. So it's treating it like a cash outflow because you're reinvesting back to bank. Really, you're just leaving it there. Right, so you leave that $100 in, it earns another $5 in interest, you draw it off, and that just goes on forever. As long as you leave that $100 in the bank, you got it. Right, so we can create this. So suppose, if you like, this bank account exists, right? Let's just take that as a given right now. You can create this perpetuity. Suppose somebody out there wants to sell you a perpetuity as an investment. Right? It's a $5 perpetuity. Right? You can purchase it today, and this investment will pay you $5 per year forever. How much would you be willing to pay for that perpetuity? Would you be willing to pay $200 for it today? Why not? You might as well keep your money. Yeah, well, you can create that perpetuity yourself for $100. Right? So if you were looking for a place to park cash to earn some rate of return, it is a 5% rate of return. Right? Maybe that's the best you can do. Hell, that's pretty darn good right at the moment for a secure investment. You can create the perpetuity yourself for $100. So you would be unwilling to pay any more than $100 for it. If they tried to charge you $105 for it, you wouldn't take it. You just create it yourself in the bank. Right? If they tried to sell it to you for $90, well, now that's a greater rate of return than the bank's offering you, and it looks more attractive. Right? So the price of this perpetuity in the marketplace, if it exists, if the British government tried to sell consoles today, and the going rate was 5%, it could charge more than $100. Right? That whole arbitrage stuff, the law of one price, competitive marketplace, the price of equivalent goods must be pretty darn close. If this perpetuity exists, the price must be $100. Okay, so if we wanted to generalize this so there weren't just cash flows, we're going to call the principal amount P, the interest rate R, and the cash cash flow is C, so every year we can withdraw the interest we earn, which is this cash flow C, by taking the principal amount times the interest rate. Right? We're going to work examples with this. I'm just trying to get you a picture. And we leave the principal amount P in a bank. Right? Cost of creating that perpetuity is the amount of principal we put in, P, right? So the value of receiving that cash flow C in perpetuity is the upfront cost. That is the principal that we put in. So that $100 is the cost of the perpetuity. Let's Okay, so let's play with this a little bit. We know that find the cash flow of a perpetuity, which we're going to call C. We take the interest rate, we call R, and multiply by the principal. We're going to call P, right? So the cash flow is equal to the interest rate times the principal amount. So using this, then, the value of a perpetuity that is the principal needed to create cash flow C in perpetuity is P, that principal amount that we would have to deposit. Right? So the value of this thing at any given point in time, we just resolve this equation for P. Right? So we're going to divide R to the other side. It's going to be the cash flow divided by R. So an equivalent way to state this the present value of a perpetuity of cash flow C at interest rate R is, so now I'm going to use PV for present value instead of the principal amount, just the cash flow divided by the interest rate. Alright, so the present value of perpetuity of cash flow C with an interest rate of R is just the cash flow divided by the interest rate. memorize the formulas on the formula sheet as we go through these, because we're going to collect a lot of formulas in this chapter. So the present value of perpetuity is right here on your formula sheet. Have you guys found the formula sheet on my finance lab yet? Okay.
I don't like one.
The formula sheet posted on Blackboard. I thought I hid that. I need to go back and look at that and make sure it's correct. Alright, this formula sheet that is on My Finance Lab, when you log into there, once you go through Blackboard and get into My Finance Lab, you go to document sharing. It pulls up that list of folders. One of the folders is formula sheet. Right here, you've got a Word document that's a formula sheet. This is the exact same formula sheet that the proctor's going to hand you when you walk in the testing center. Right? You can't bring your own inside of there, because you can scribble stuff on it, put extra notes on it, what have you. They just can't let you bring paper to the testing center. But I would recommend going ahead and downloading this, printing it off, and working your homework problems with it so you get used to finding the formulas on there. You don't have to memorize any formulas, but you will have to rearrange some of these to serve your purposes. I don't have every possible formulation of every formula on there. It's just usually the basic ones. So you may have to wiggle them around a little bit. So you want to get used to that before you sit for a test.
What was that email that you sent us about the testing center hiring stuff?
I'll send another email about that and talk about that a little bit before we get started. We're still working on it. Okay, once you get that formula sheet, it's broken down by chapters. Go to chapter 4, and the present value of perpetuity. Just C divided by R, where C is the cash flow and R is the interest rate. Alright, so same thing we're working with. Alright, let's look at. Oh, yeah. Alright, excellent. Let's look at number 6 from the chapter 4 homework. And I'll use my homework problem so your numbers will be a little bit different. Just stretching.
Oh, yeah.
Yeah, okay. You want to endow a scholarship that will pay $10,000 per year forever, starting 1 year from now. If the school's endowment discount rate is 7%, so that's what they can earn their investment, 7%. What amount must you donate to endow the scholarship? All right, let me throw this over here and we'll put up all of our numbers. So here's what we want to create. Here, I'm going to draw it out on the timeline. Remember, get in the habit of drawing these timelines with the simple problems, and your life is going to be so much better when we get into chapter 5 later. Alright, so what we want to do is endow a scholarship that will pay $10,000 per year forever. So we want it to throw off $10,000. Remember, perpetuity, the cash flow starts 1 period from now. That's right, and we want that to go on forever. And the question it's asking is, how much must we deposit today to make this happen if the school can earn 7% on their investments? So from the definition, what that is equivalently asking is, what is the present value of a cash flow of $10,000 per year forever, given an interest rate of 7%? Right, those two questions are exactly the same. How much must we deposit today? It's the same as asking, what is the present value of this perpetuity? Right, we've got our handy present value of perpetuity formula. So I'm going to say present value. And here I'm going to get in the habit of putting subscripts on my terms so that I'm very careful about knowing when the cash flows are actually occurring. I'm going to put PV sub 0 on there. I wanted to make make a joke about Mortal Kombat. You guys want to play Mortal Kombat? I age myself again. All right. Excellent. All right, so present value sub-zero means at time period 0. So I'm finding the present value of these cash flows as of time period 0 the way I define it on my timeline. All right, so in order to find that, I'm going to take the cash flow divided by the interest rate. Right, my formula for the present value of perpetuity. The cash flow is $10,000. The interest rate is 7%. Need to express it as a decimal. Plugging it into the formula, so it's 0.07. And I'm not quick enough to do that in my head, so let's see. 10,000 divided by 0.07 equals $142,857.14. It's going to ask for nearest cent. Yeah. All right, so if I wanted to create this scholarship of $10,000 per year forever, I would need to today, right now, deposit $142,000, $143,000. Roughly to that bank account to create this scholarship. If you guys are in a position to do that, you can make the checks out. See Excel, I'll make sure they get the right ones. All right, let's double check that. 142,857. All right. Okay, questions on that one? We okay? All right. Let's make it slightly more interesting, but not that much. All right, let's talk about a growing perpetuity. Okay, a growing perpetuity, much like a regular perpetuity, has a stream of cash flows that occur at regular intervals. But here's the wrinkle with these. They have stream of cash flows that occur at regular intervals and grow at a constant rate forever. All right, so if we were looking at a generic timeline of these things, it would look like this. We have cash flow C at time period 1, but then at time period 2, we would have cash flow C times 1 plus G, where G is our growth rate. It grows by whatever that rate is. Is the growth rate in cash flow. The growth rate of the cash flow. At time period 3 then would be C times 1 plus G squared. It grows twice. Or C times 1 plus G third. It grows 3 times. And then that would just continue in perpetuity forever. So it's a little bit disingenuous when I talk about your professor's salaries being set up as perpetuities. Usually they're set up like this because there's going to be a rate of inflation that you want to compensate for over 10, 20, 30-year periods. Normally they're set up as growing perpetuities to account for the rate of inflation. Or they should be anyway. If they're not going to be worth much otherwise. Right, to find the present value of these things, it's almost as simple. We're just going to take the cash flow divided by, now instead of just the rate, it's going to be the rate, the interest rate minus the growth rate. Believe it or not, that's a part there. Okay, so we still take the cash flow and divide it by a rate, but now it's the interest rate minus the growth rate. So account for that growth rate.
Why do you need to know the present value? I mean, like getting a raise every year and then just deposit more money every year. You're not gonna know how much, like, why do you need to know the present value?
Oh, that's a good question. Why do you need to know the present value? Okay, so let's say I win the lottery in higher education fortune. I decide I want to go now, the Stelk chair of finance, University of Southern Mississippi, right? I'm gonna go retire and live in Hawaii, but I want to make sure people can still teach here. So how much would I need to deposit today to guarantee a salary of X number of dollars in real terms forever? So I would need to know how much to deposit today. That's the present value of the growing perpetuity. Question. All right, let's look at an example of this one. And let's see, we're going to use number 11 from chapter 4. From page 4-23. So the setup for number 11 says a rich relative is bequeathed you a growing perpetuity, like you. The first payment will occur in a year and will be $4,000. Each year after that, you will receive a payment on the anniversary of the last payment that is 4% larger than the last payment. This pattern of payments will go on forever. Assume the interest rate is 16% per year. Nice. What is the value of today's bequest? What is the value of bequest immediately after the first payment is made? Okay. So let's map out the numbers as they exist in my problem. I'm going to want to know the present value. First payment occurs in 1 year, and how much in my problem? $4,000. Each payment is going to be 4% larger than the last one. So my payment 2 years from now is going to be that original $4,000, but then it's going to grow by 4%. So I'm going to multiply it times 1.04 to grow at 4%. You guys okay with what I'm doing there? Can you go back and look at the compounding thing we looked at last class? Okay. 1 year after that, that same $4,000 payment will have grown at 4% twice. And that pattern is just going to go on forever. Right, and it's going to ask us 2 questions with this. Part A is what is today's value of the bequest? And why do you want to know that? Maybe you want to sell it, right? You don't want to sit and wait for those cash flows to come in every year. You want to get paid right now. So you you want to sell that security off to someone else. We got to come up with a price, right? So we're going to find the present value of it. So the first thing we're going to do is find the present value as of time period 0, the value, today's value of the bequest. Right? So that's the cash flow divided by the interest rate minus the discount rate. Right, this formula, just like the one for a regular perpetuity, when you use a cash flow, whatever cash flow you plug in, you're finding the present value one period before that cash flow. Right, so I'm also going to stick a subscript 1 on that C. Right, so I know that I'm using cash flow 1, that is the cash flow that occurs at the end of year 1, and that's going to give me the present value as of the end of year 0. The construction of this formula is exactly like the one from the regular perpetuity. It's just a lot more convoluted to go through setting it up. You get a bunch of algebra and canceling out, but it does the exact same thing. It's always giving you the present value one period before. Okay, so when I plug in that $4,000 payment, that cash flow that happens at the end of the first year, it's giving me the present value 1 year before that. All right, my interest rate, it tells me in the problem is 16%. Then to subtract from that the growth rate in payments, 4%. And this is one that will give folks a lot of trouble when you first start working it. The order of operations will get you here. If you just plug this into your calculator as 4,000 divided by 0.16 minus 0.04, it's going to do division first and then subtraction. It's going to follow the correct order of operations. Right? Multiplication division happens first, then addition and subtraction. So we have to be careful how we do this. I put parentheses around the denominator to make sure that we do this subtraction first before the division. Right, so when you actually plug this in, you can plug it in as it exists right there, or you can go ahead and do the subtraction. The 4,000 divided by 1. Right, so the present value as of time period 0. So if you wanted to sell this thing today to someone else and you guys decided that 16% was the appropriate discount rate, then it would be worth $33,000 and change. What? You guys okay with coming up with that number? Good? Okay. Part B changes the question on us a little bit. What is the value of the payment immediately after the first, or what is the value of the request, immediately after the first payment is made? So we're moving on the timeline now. I'm just redrawing the timeline. You don't have to do this in your notes. Just don't want it to get you jumbled. All right, we initially found the present value as of time period 0. Now we're looking for it immediately after the first payment is made. So now you've received the first payment of $4,000. Now you decide you want to sell this thing to someone else, right? Because instead of waiting for $4,000 a year, you'd rather just get a lump sum up front. All right, so this payment is gone, right? That initial $4,000. It's been paid to you, you've got it. But you want to sell this thing now. So what you're looking for is the present value as of the end of year 1. So I'm going to put PV sub 1 on that. The first payment that someone would receive off of this thing, if they bought it from you, is this $4,000 times 1.04, the one that's 4% larger. So now we want to find the present value of the stream of payments that are left. Right, so in this case, we're looking for the present value as of the end of year 1. That means we need to use the cash flow at the end of year 2. Need that cash flow that's 1 period later. R minus G doesn't change. Alright, so now we're using $4,000 times 1.04. Still divided by 6 minus 0.84. Okay, and same idea applies here in the denominator. Be really careful and do your subtraction first before you try the division. Right, and before I type anything in, should the present value go up or go down? Should be going up, right? The denominator is exactly the same. The numerator is now larger by 4%. Right, so it should increase. In fact, if they will, that goes up by 4%. Check that in a second. So 4,000 times 1.84 divided by 0.12. Now, 34,000. Equal number. Alright, just for giggles, no reason you have to do this. The math nerd coming out. I'm going to take that original answer and I'm going to multiply it times 1.04 so you get the same thing. Alright, you guys okay that are punching the calculator and go along and getting these numbers to come out okay? For yourself?
Okay.
There'll be at least one class where they determine on.
Yeah, I was trying to download the calculator and some video popped up.
Okay, you guys, humor me. I'm going to hit similar exercise on this, so give us a blank problem. You guys try to practice run with this one, because I end up answering so many questions about why the numbers are coming out wrong on this particular question that I like to get a rep in right here while I'm standing here.
Okay.
Someone's got the answers for that. Which guy? Got 30,000 for part A. Yes, right? Anyone else get 30,000 for part A?
I got it.
Okay, anybody else got part B?
31,500.
31,500. Anybody get anything different? Okay, if you're not getting those, shout right now. You're not alone. Everyone else is too afraid to say anything, because I can tell you how many emails I answer on this question every semester. We're okay on this one? All right. to a different type of cash flow, and this is one that we're all probably intimately familiar with at this point already. We're just going to name it. Let's talk about annuities. Does anyone already know what an annuity is?
At the end, it's a private limited company that has an end.
It's like a perpetuity but it has an end. So it's like a perpetuity in that you've got regular cash flows happening at regular intervals at a fixed amount. So it's the same cash flow at regular intervals, but it ends, right? Instead of going on forever, it just has an end. Sounds an awful lot like a car note, right? You have a fixed monthly payment for however many years you got the note, and it's done. It ends at some point. So a lot of our contracts, like this mortgages, leases, all kinds of stuff, are very much annuities. Right, so quick textbook definition, string of n equal cash flows paid at regular intervals. We can actually go through and construct one of these. We can build a generic one just like we did with a perpetuity and then play some algebra games and rearrange it. And what we'll end up with is a present value of an annuity formula that looks like this. Right, so present value. It's going to be equal to the cash flow times 1 over the interest rate. That's times 1 minus 1 over 1 plus the interest rate raised to n. Label all those parts. C is the cash flow, R is the interest rate. N is the number of payments in the annuity. Right, and the part I skipped over, which is why I hesitated, is this is the formula for the present value of an ordinary annuity. Okay, an ordinary annuity means payments occur at the end of the period. Those financing arrangements that we're familiar with are set up as ordinary annuities. Right? When you pay your car note, you're actually paying at the end of the month, the end of the period, for the use of the money over that time period. Avoiding the ordinary annuity. Some are what we call annuity due. Right? That is, you pay at the beginning of the period. Most leases are actually like that. Rent is due in the first of the month, right? And that's so you can remain in the the apartment over that month, you don't pay rent that month, they can kick you out. Right? You're not paying for the month you're in there, you're paying for the month coming up. Most cable contracts are like that too. You actually prepay for the month of use. All right, we'll look at those in just a second. All right, so that present value of an annuity, that formula is on your formula sheet, of course. So the present value of ordinary annuity has several formulations. You've got it on your formula sheet right here. Written two different ways. But it's there, you don't have to memorize it. That one's kind of a beast. Right? Yeah. All right, since an annuity ends, it has some terminal value. It makes some sense to talk about the future value of an annuity. All right, so on your formula sheet, you have that formula as well, at least for an ordinary annuity. And all you really do, I'm going to point this out, and then we'll look at the simple version of this formula. Right here, that guy right there is the same formula as the present value of an ordinary annuity. Right, it's the same thing we just wrote down in a little bit different way. Right? And then we're going to multiply that times 1 plus r to the n, right? That is, we're just going to compound it in periods into the future. So it's nothing but a lump sum future value formula, right? That's all it's done. It's taking the present value of an ordinary annuity and then multiplying it by your interest rate factor to run it into the future. When you multiply that stuff out and cancel some stuff, it ends up looking like this. It's a much simpler formula. Right? So we could also have the future value of an ordinary annuity. So the future value of an ordinary annuity ends up looking like this. C divided by R times 1 plus R n. So let's play with these. Let's do number 7 from the chapter 4 homework. And that is problem K 4-16. Number 7 says your grandmother's been putting $2,000 into a savings account on every birthday since your first. That is when you turn 1. The account pays an interest rate of 9%. How much money will be in the account immediately after your grandmother makes the deposit on your 18th birthday? Okay, so let's map out what we know. When we were born, she paid nothing. The first year of our life, right, on our first birthday, the end of our first year of life, she deposited $2,000 in the savings account, right? It says on every birthday since your first, that is when you turn 1. And the account pays 9% interest. How much money will be in the account immediately after the grandmother makes a deposit on your 18th birthday? All right, so second birthday, she dropped another $2,000 in there. Okay, and I'm going to do something with my timeline. Instead of drawing out 18 years worth of $2,000 payments, I'm going to do a little squiggle in there, which means the same stuff happens in the middle. And then on her 18th birthday, there's another $2,000 deposit. And what we want to know is immediately after making that 18th deposit into the bank, right? So I want to know the future value end of year 18. How much is sitting in my bank account? How big of a party can I throw when I graduate high school? Okay, to get practice, let's actually do this. Let's do it the easiest way first, and then I want to get some practice using the present value formula as well. All right, so let's start by plugging directly into the future value of an annuity formula. Right, this is an ordinary annuity. Right, at time period 0, nothing happened. The first payment occurred at the end of the first year. Right, so we use the ordinary annuity formula. And that guy is our cash flow divided by the interest rate times the quantity, 1 plus R. So if we plug in all the cash flows we know from this problem, or all the information we know from this problem, the cash flow is 2,000. Interest rate tells us is 9%. For plug in 0.09. Multiply that times 1 plus our interest rates. When I write this down, I'm going to go ahead and do the addition so I can save myself that possible mistake in the calculator. Add them together. So 1 plus R, the interest rate is 0.09. We're just going to write it as 1.09. In 18, we're receiving 18 total payments. You guys use your calculators however you want. What I'm going to show you is my incredibly OCD way of working these kind of problems. Because if you're like me, you're going to get somewhere 2/3 of the way through entering this thing, and you're going to fat finger something. Right? You're going to mistype something going in there, and you won't realize it. Your answer will be garbage coming out. I have no idea that's the case. Okay, so I like to break it down into smaller chunks and store values as I go. So here's how I'm going to do it. I'm going to start with 2,000 divided by 0.09. I'm going to type equals. Right, so that turns out to be 22,222.22 repeating. Alright, now that value, while it's sitting on my calculator screen, it's only showing me 4 decimal places because that's all I've asked it to show me. That's how I set it up. It's worked out to 13 decimal places, no matter what it's showing. Right, so what I want to do is, while that's on the display, I'm going to store that value on one of my numerical keys. And it's going to store the full 13 decimal version of that answer. Right, in order to do that, while that number's on the screen, I'm going to hit the STO key, which is just the left of the 4. And then I'm going to press the number 1 key. And what that did is it just stored the full 13 decimal version of that number on the number 1 key for me, and I can recall it anytime I want, the full number. Right? Instead of just writing down 22,222.22 and then plugging that in again later and introducing that rounding error, now I've got the 13 decimal version stored. Right? And you can store numbers on any of the numerical keys 0 through 9. I'm in the habit of starting at 1 and working my way up for every problem. There's no reason you have to go that way. You can sort of any key. Okay, so store 1, if I clear that out, I can hit recall RCL, which is right below the store key, or right across from the 1. Hit the number 1 key, and there it is again. And again, showing me 4 decimal places, but it's actually stored the 13 decimal version of that answer. So I've eliminated my rounding error for the most part. All right, now let's to move on to the second part of this problem. All right, 1.09 raised to 18 minus 1. I'm going to clear everything out and just enter that all by itself. 1.09. Once 1.09 is on the screen, I'm going to type y to the x to raise it to a power. And now I can enter the power of 18. And then I'll say minus. Notice it goes ahead and does the exponent for me because that comes before subtraction. 1 equals 7, 1, 7, 1. And I'm going to store that on the 2 key. Right, now I've got both of those. I can do recall 1 times recall 2 equals all that good stuff. Six around 8. Alright, let's see if that's what it's looking for first. Alright. Okay, you guys are following along. You getting those numbers to come out okay? If you're committing to the BA2 plus at this point, it's worth practicing these a couple of times so you don't use rounding errors. And again, in the testing center, you're welcome to bring in a scientific calculator if you're more comfortable using for this kind of stuff. It'll be fine. Just no graphing calculators or anything that has USB input. Right, any questions on that? Okay.
Our decimal place it.
You got the same numbers as your decimal in a different place?
No, like my after the decimal is just 0.2222.
On the first part here?
I'm gonna ask.
For the answer.
Okay, let me see what she has to do. Okay, that's why. So yeah, you guys, we need to store that second value at 3.7171. When you just type in the 4 decimal approximation, you're introducing that rounding error. So when you calculate that number, you want to store it as well, and then multiply the stored values together. All right, let's look at one that has us calculating instead of the future value of the annuity, the present value of the annuity. I'm sorry I can't make this text bigger, guys. I'm stuck. They're still creating this in Flash, so I have very little control over it. All right, so let's look at number 10 from chapter 4. This one's says, you figure the total cost of college will be $96,000 per year, 18 years from today. Yeah, those of you that are looking to have kids and want to fund their college education, this ain't all that far off. If I apply the existing rate of inflation to college tuition, I'm going to be paying over $100,000 a year per kid by the time my 5-year-old's in college. So don't go, it's hopefully the rate of inflation won't. Or my kids will be going to the military to college. Okay, so you figure the total cost of going to college will be $96,000 per year. 18 years from today. If your discount rate is 4% compounded annually, what is the present value today of 4 years of college costs starting 18 years from today? Whoa. All right. There's a lot going on now. All right, let's map out our timeline because there's some timing funkiness happening. All right, so I'm going to do years 1, 2. I'm going to do my little squiggly here, and I'm going to start with year 17. I'll tell you why in a second. $18 years from today is when we think we're going to have to start paying those college costs. That's when we have the first $96,000 payment. Okay, and we're going to have that for 4 years, assuming we can get somebody through college in 4 years. As you all know well, that's increasingly less common. I'm a 4.5-year graduate myself. All right, we're going to encounter those costs for 4 years. Then they're going to stop. Notice the interest rate is 4%. Okay, this is what my timeline looks like. Starting 18 years from today, I think I'm going to have to pay $96,000 per year for 4 years. What I want to know is, what is that in today's dollars? If I want to go ahead and set up an account, send my kids to college in 18 years, how much do I have to deposit today to make that happen? All right, so what I want to know eventually is the present value as of time period 0. Okay, today. Well, I have an annuity, right? I've got 4 level payments of $96,000 that stop. This is an annuity, so I can use my present value of an annuity formula. The trouble is, I have in between now and 18 years, I have 17 years of zeros. Right? So I can't directly apply my present value annuity formula because I don't have a level payment over these 21 years. It's level at 0 for the first 17, and then it's level at 96,000 for the next 4, right? Years 18 to 21. All right, so I really have 2 different annuities. One's a 0 for 17 years, and then the second one is the 4 payments of $96,000. So I've got to break this into 2 steps. I need to find the present value as of end of year 17 for the $96,000 annuity. Starting at the end of year 18. Okay, why end of year 17? Because that present value annuity formula, just like your perpetuity formulas, is always giving you the present value 1 period before the first payment occurs. Right? So when you plug into that present value annuity formula, it's going to bring it back 1 year. Right? And it will only bring it back 1 year. It's going to take those 4 payments and bring them back to the time period before the very first payment. So I've got to do that. I'm going to get a lump sum. I'm going to figure out what that annuity is worth, and I'm going to run that amount back 17 years. All right, so we want to use the present value of an annuity formula. I want to be really careful here and make sure that I know I'm getting the present value as of the end of year 17. Because I'm using cash flow, the first cash flow I plug in is at the end of year 18. And those of you guys that are already using the formula sheet, it's written slightly different on your formula sheet. Instead of doing C times 1 over R, it just goes ahead and divides C by R. Those are exactly the same thing. All right, so it's written like this in the formula sheet. Okay, so let's plug in what we know. We've got the $96,000 cash flow at the end of year 18. That's divided by our interest rate. Given to us in the problem of 4%. And then we're going to multiply that times 1 over 1 minus 1 plus the interest rate, which I'll go ahead and write as 1.04. That's okay, and that 1.04 is raised to the n. You guys remember what n is? It's the number of payments. How many payments are in this annuity? 4. Right, there are 4 payments of $96,000. We're only finding the present value of that 4 payment annuity first. Right, I'm going to work this one the same way, storing values as I go. So I don't have a rounding error, and I can go back and find my mistakes when I inevitably make one. 1,000 divided by 0.04 equals 4. I'm going to write in my notes STO1 to know that I'm storing that on the 1 key. STO1. That overwrites what I had there before. Alright, now I'm going to do the part within the parentheses. So 1 minus 1 divided by 1, 4, y to the x to the 4th. Do all that stuff in the right order for me. And put 1452, and every bit is important. I'm going to store this value. I'm going to store the full 13 decimal version of that value on the 2 key. So when I multiply these two together, I don't get a rounding error. All right, so the present value as of the end of year 17, this annuity is $348,469.94. And however you're working this problem, store this value. So we're not done yet. We do not want to introduce a rounding error. STO3. Every time you get done with a problem or with a chunk of a problem, always take a step back. It's so easy to get lost staring at the trees and forget what the forest looks like with these, because you're doing so much formulas and numbers. All right, I was finding the present value as of end of year 17 of a stream of 4 payments of $96,000. Right, if I just add those up, and I don't worry about discounting, each one is something just under $100,000, right? So my total should be just under $400,000. If I just add them up. I'm finding the present value of them, so I'm discounting It should be something even smaller than that. So when I look at my answer and I say, all right, I came up with $348,469. Does that look good? Is that about what I was expecting? I was expecting something a little under $400,000. That looks about right. All right, I think I'm on the right track. If you come up with something that's $600,000, right, you know you're way off. Because if you were just adding cash flows up, it'd be less than that. If you come up with something that's like $3,000, you know you're way off. Okay? So always worth just kind of stopping and making sure we're on the right track. All right, before we go to the next step, you guys get this number to come out okay? We're good? All right. All right, so what we've done, 348, 469, we have found, as of end of year 17, the value of 4 years of college. So if I wanted to wait 17 years and then deposit money in the account, I need to deposit almost $350,000 in order to make sure my kid can go to college for 4 years. Right? That's going to suck. But luckily, I'm starting now instead of 17 years from now. So I want to know the cost today. I still need to take that $348,000 and I need to bring it back 17 years to time period 0. But now it's just a lump sum. Right? I've got the value of that entire annuity as of the end of year 17. So in the second step, we want to find the present value as of today, actually as of, let's say, year 0. Of the above annuity. So I want to find the present value as of time period 0. Now it's just a lump sum, so I'm going to take the future value, which is end of year $17, so I'm going to just be consistent, divided by 1 plus my interest rate, raised to n, right, where n is again the number of periods. This is what you did all through chapter 3. Right, so I'm going to take that future value of $348,000 change and divide it by 1.04. This time raised to the 17th, so bring it back 17 years.
Using the old present day, so chapter.
Yep, you got it. And use an old present value. So I've converted that stream of payments now into one lump sum. And that lump sum is what we're working with off of chapter 3. Alright, so present value as of year 0. When I go to my calculator, I've stored that value on the 3 key. Right, instead of just retyping in what I wrote down in my notes, I'm going to hit recall 3. It's showing me 4 decimal places, but it's using 13. So I eliminate that rounding error. Divided by 1.84, y to the x, 17 equals $178,895 and roughly 15 cents. Alright, so instead of having to fund a $350,000 bill 17 years from now, I can deposit $179,000-ish today. And have it covered. Let's make sure that's actually right. Not always guaranteed. you guys are following along. Are the numbers coming out okay? Couple of steps in that one. Are you guys okay with why we're doing what we do? Any questions? Why or alright, so ready to move on to some more fun then? Alright. This one's gonna be even funner. I apologize up front. Alright, so we talked about perpetuities, growing perpetuities, annuities. Now we're gonna talk about growing annuities. And growing annuities, a stream of growing cash flows. Paid at regular intervals. And growing at a constant rate. Right, with annuities, we looked at both present value and future value and calculate both of those easy enough. With a growing annuity, it turns out there's not a nice, neat, what we call closed form solution for the future value of an annuity. We can only calculate the present value of that guy. Right, so the present value of a growing annuity is this critter right here. C times 1 over R minus G, right? Same adjustment we made for a growing perpetuity before. And then times the quantity, 1 minus 1 plus G over 1 plus R. That whole thing raised to the n. That. Again, not one you have to memorize. You've got it on your formula sheet. We've also got a formula for the future value of a growing annuity on there that another instructor must have added. I'm awfully suspicious of that formula. But that's all I will play with. Okay, let's play with one of these guys, although we'll go through it kind of quick because at this point, I usually use this one as an example of how to use the store and recall options on a calculator. You guys have seen it now. So we can go very quickly to this one. All right, let's look at number 13 real quick. so the setup for number 13 says you work for a pharmaceutical company that has developed a new drug. The patent on the drug will last 17 years. You expect the drug's profits will be $4 million in its first year, and this amount will grow at a rate of 3% per year for the next 17 years. Once the patent expires, other pharmaceutical companies will be able to produce the same drug, and competition will likely drive profits to zero. What is the present value of the new drug if the interest rate is 10% per year? All right, let's map out what we know from this problem. Here, 17 years on this problem. Okay, you expect the drug's profits will be $4 million in its first year. So by the end of the first year, you think you will have earned $4 million. And let's see, I'm going to look ahead to the answer. I can see that it wants it in millions, so I'm going to work with millions. We'll put 4 right there as 4 million. All right, profits of the drug's first year will be 4 million, and that amount will grow at 3% per year for 17 years. So year 2, that $4 is going to grow by 1.03. So let me write out another year on the timeline, just to make sure you got this. End of year 3, that $4 million profit will grow 2 times. Right? And if I'm mapping out that payment at the end, that $4 million payment would have grown at 3%, 16 total times. You got it, right? The superscript on your exponent is 1 below the year that it's attached to. All right, after that, profits are driven to zero. This thing is essentially worthless for us. Right? What we want to know is, what is this worth today? So we can take all of these payments and drive them back to time period $0, and we're going to use a discount rate of 10%. So we want to know the present value as of end of year 2. Right, well, this is a growing annuity. We've got payments happening at regular intervals that end, and they're growing at a constant rate over that time period. So we've got to use the present value of a growing annuity formula. So present value as of time period 0. There's no funky adjustments for this one. We're just going to use cash flow 1 times 1 over R minus G. And that times quantity 1 minus 1 plus G. R raised to the n. And those of you guys that have been to another finance class or are working ahead and are using the time value keys in your calculator that I haven't showed you yet, won't work on this one. Time value keys can't handle a growing annuity. Got to go formula and algebra for this one. All right, so let's plug in what we know. That first cash flow is $4 million. That's going to be divided by my discount rate of 10%. Minus my growth rate of 3%. All right, and that is going to be multiplied by the quantity. Right, I'm going to save myself some potential missteps in typing this into the calculator by doing some addition when I write it down. I have 1 plus G, 1 plus my growth rate is going to be 1.03, and that's going to be divided by 1 plus my discount rate, 1.1. And I'm going to raise that entire quantity to n, which is the number of payments in this annuity. And so I'm raising that thing to the 17th, not the 16th. It's up here, but n, just like before, is the number of Alright, so that's enough work, just collecting all the information to put it in the formula. You guys okay so far? Okay. Hang with me for another 3 minutes while we work through this one. The other example would be a total piece of cake. You're gonna like the rest of it. Okay, I'm gonna work this one left to right, storing values as I go. Rounding errors, because we're using such tiny numbers and raising to such high exponents, are gonna crush you on this one, as we want to use stored values. Let's see, 4 divided by, if I want to make the calculator do this work for me instead of doing it in my head, I need to open parentheses. 1 minus 0.03, and close parentheses, and we'll do that subtraction for me. That is 57.1429. Remember, that's in millions, so the stuff to the right of that decimal is significant. Right? We don't want to lose it. Store that on the 1 key. Store 1. Right, and then that's going to be times. So, parentheses. 1 minus open parentheses. 1, 2. Six, 7, 4, 2.
So on the calculator, do you do 1 minus open parentheses 1.03 divided by 1.10 close parentheses to the 17?
That's it. Yes, exactly right. Yeah, I type it in exactly as it's written there. Yeah, you got it. So I'm getting 38.4. What's it looking for? Around the 3 decimal places. So 38.457. You guys are following along and getting the same thing? Okay, so this one I'll go ahead and warn you, this is probably the most difficult thing you have to do in chapter 4 is working through this formula, and it takes reps, right? It's gonna feel like you're trying to learn how to wipe your bottom with your offhand, right? Your right hand and your left hand. So it's gonna feel like the first few times. Right? But I promise after you do it for a little while, it's gonna be second nature. You're not gonna have a problem working through this. Go on to the other examples. It's gonna work one where we need to go. But any questions on why we're plugging in, what we're plugging in on this one? Get it to come out okay? Questions on why we're having so much fun? Okay, that's really it, guys. For the types of cash flows that we have, you've got lump sums, you've got perpetuities, growing perpetuities, annuities, and growing annuities, and some sub-flavors within those, right? We've got ordinary annuities and annuities. But that's really it. Those are the only kind of cash flows that you can have. If you have an unequal cash flow stream, like it changes every single year, well, that's just a series of lump sum cash flows. There's not a formula that can save you there. You gotta go one by one. Right? But you now know how to deal with every single type of cash flow that exists in the world. Got it? Okay. It's just a matter of applying it now. What we haven't done is done things like solve for the rate of return on something, or the number of payments required to pay off the loan. Right? So we haven't solved for R, we haven't solved for N, and we haven't solved for the payment on annuity. Right? Chapter 4 asks you to do some of those things. So I want to look at some of those examples. Just while I'm doing that one, much like many of us did. All right, let's start by solving for R. Let's look at from the chapter 4 homework, number 14.
Are the tests gonna be 60 questions? I'm sorry.
Oh, no, good question. Tests are 25 questions.
Okay.
25 questions. Yep, I know we got it coming up next week, guys. As soon as I nail down what's happening with the testing center, I'm going to send an email with all of the exam setup stuff. Like how many questions, the breakdown of what questions comes from what chapters, all that stuff. I got it typed up, I just want to know what the testing center is. Okay, so here's the setup for number 14. You're thinking about buying a savings bond. The bond costs $50 today, will mature in 10 years with a value of $100. What annual interest rate will the bond earn? Okay, let's map this guy out. Today it costs $50. And it's a savings bond. We're not all that familiar with those these days, but what happens is you buy it today and then nothing happens until it matures. Right, it matures 10 years from now and pays $100. Okay, and the question is, what is R? What's your rate of return? How do I figure that out? Because we've actually already done all of this, we just haven't looked at it from this angle. What is your, okay, let's actually go back to the question real quick. You're right, it doubled. But what it asks is, what is your annual interest rate? So what you earn per year, not the total interest rate. What about the effects of compounding? Yeah. How can I figure this out? Okay, let's start here. What type of cash flow is this? Annuity, perpetuity, lump sum?
I don't know.
Is it a series of level cash flows happening at equal intervals? Not right. So all the annuities and perpetuities are gone. So what's left? It's a lump sum, right? What formulas do I have for working with a lump sum? Yeah, what's that present value equation look like? PV equals what? Okay, looking at that formula, what pieces of that do I know? Do I know the present value? I know what it is today, right? Do I know the future value? Yeah, I know it's going to pay 10 years from now. Do I know the number of periods? Yeah, what's the only part I don't know? R. Alright, so let's plug in what we know and solve for this thing. So the present value is $50. Future value is 100. 1 plus R, and that thing is raised to 10. Alright, so I got to be able to solve for that R. What that thing will tell me is what is the rate of interest, including the effects of compounding. So it's going to tell me my compound interest rate. That's simple. So let's play some algebra games. I'm going to multiply both sides by 1 plus R. And it looks like that, right? And here, let me write it all down so we know what's going on. Okay, so I'm going to multiply the right-hand side by 1 plus R to 10. there. We gotta do the same thing to the other side. Put those over there, right? I'm going to divide both sides by 50. Right, so it cancels out on the left. Left with 1 plus r to the 10 over 50. Hey, we're in an exponent. Do you remember how to do that? I'm going to take the root. Right? But not just any old root. I've got to take the 10th root of that thing to cancel it out because it's raised as 10. So I need to take the 10th root of both sides, which cancels them out there. So I'm left with 1 plus r on the left. And on the right, I've got 100 over 50. I've got the 10th root of that. Another way to write that is raised to the 1 over 10. Now I've just got that pesky 1 on the left-hand side, so I'm going to subtract 1 from both sides. So I'm left with, let's cancel out, r equals 100 over 50 raised to the 1 over 10 minus 1. Again, if you guys are committed to using the VA2 plus, it's a little bit funkier than using a scientific calculator, but it can still be done pretty easily. So the way I would enter this is, supposing I had weirder numbers than 100 divided by 50, I can get out of my head, but let's go ahead and type it anyway. 100 divided by 50, and I'll press equals to make it go ahead and do the division for me, or I could have put it inside parentheses. Well, once I've got that division done, I'm going to type y to the x, and then I'm going to open parentheses and do 1 divided by 10, close parentheses. I can do that division and then type equals. Alright, so I'm going to write that out. We've all got it. R equals 100 divided by 50. And the VA2 plus, I'm going to type the y to the x key, open parentheses, 1 divided by 10, close parentheses, minus 1. So 718. Sure, it wants that as a percentage. It does. Or 7.18%. Right. Okay, and I think we did, let me look on here, we ended up adding this stuff. Yeah, we did. So on your formula sheet, you actually have that thing solved for R for you. Right there. Alright, if we go back and look at what we've done, that R is actually, alright, looking at this, that R is actually your future value divided by the present value, raised to the 1 over n minus 1. That's what you got. formula's a little funky. I'll let you guys play with it. It's not that big a deal. Solving for n though gets a little funky. Alright, let's look at chapter 4 homework 19. Alright, number 19 says you receive a $6,000 check from your grandparents for graduation. You decide to save it toward a down payment on a house. You invest it earning 11% per year. Nice. And you think you will need to have $12,000 saved for the down payment. How long will it be before the 6,000 has grown to 12,000? Okay. So what do we know here? We know at time period 0 we received $6,000. We're going to deposit that in our bank. There's going to be no other cash flows. We're going to let it sit for some n number of periods, and we want it to have grown to 12,000. Right? We know the interest rate we're earning is 11%. From there to there. So the question is, how long does it take before that happens? Okay, this is a lump sum deal, so we're going to use the present value, future value formula. Doesn't matter what version it is. Plug in the bits that we know and solve for n. All right, or actually, let's do that a little bit differently. Let's go ahead and solve this equation for n, right? And then plug in the parts that we know. All right, so I've got to get n by itself. The first thing I'm going to do is divide both sides by the present value. So it cancels out. On the right, I've got the future value divided by present value is equal to 1 plus r. n. Okay, here's where things get a little bit weird. That n is in the exponent. Alright, so I can play the same game I did before. I can take the nth root of it, but then on the left-hand side, I'm going to have that thing raised to the 1 over n. So I'm just putting it from the exponent on one side to the exponent on the other. It doesn't do me a lot of good. I've got to get it out of the exponent. Anybody remember how to do that? Really got to do it in calc class somewhere.
I didn't quite get that.
Yeah.
Should have done that better on purpose. Alright, if we take the log of both sides, what happens is that exponent goes out in front and gets multiplied in front of the log. Right? So that's what we're going to do. We're going to take the natural log of both sides. Right? So we do it on the left, and we do it on the right. What happens on the right, though, is that the n is at the exponent. And then it's multiplied times the log of 1 plus r. Looking familiar now? Try desperately to forget it. I like it. Alright, now I've got that n just out in front. That's what I'm solving for, so I'm going to divide both sides by the log of 1 plus r. Right, and that scribble is ln for natural log. They cancel out over there, and I'm left with n equals the natural log of the future value over the present value divided by the natural log of 1 plus r. Right, right? And again, you don't have to memorize this. We're not expecting you to do that. It's actually on your formula sheet right there. But I just want to, as often as I can in our compressed format, I want to show you this stuff isn't new. It's algebra that you picked up along the way. You probably haven't used it for a while. Okay, so for this problem, the numbers that we have, n is going to be equal to the log of what? Future value divided by present value. That's the log of 12,000 divided by 6,000 divided by the log of 1 plus r, so 1 point, what? 11%. All right, if I'm using the VA2 plus, I'm going to go inside the parentheses in the numerator first. I'm going to do 12,000 divided by 6,000 equals, they can do that division for me. And then once I've got that division done, I've got an LN key right to the left of the 7 there. Okay, I can press LN, and it's going to take the natural log of that for me. So 0.6931. I'm going to store that on the 1 key. Minimize rounding errors. All right, and then on the denominator, I'm going to do 1.11, and then press the ln key, take the natural log of that, 0.1044. Store that on the 2 key. Store 2. And then I can just do recall 1, RCL 1 to pull up that full 13 decimal version, divided by recall 2. So n equals 6.64. See if I put this in for once around the 1 decimal place, so 6.6. All right. Okay, so the only thing we haven't formally walked through an example of is solving for payments on an annuity. It's the same darn game, though. It's going to give you all of the information on annuity except the payment. You plug into the present value annuity formula and solve for it. All right. Don't delay getting into this chapter 4 stuff. I imagine what happens about an hour in, you start to kind of glaze over, everything starts to look the same. Okay. When you dig into this stuff, you're going to have some questions, almost guaranteed. Some stuff's not going to go down. So get into it as soon as you can. When you have questions about how to work a problem, throw them up on the discussion board. Let's start talking about them sometime before Wednesday night at 11 p.m. Right, or Friday night at 11 p.m. Right, so you got your homework and quiz coming up. So get into them and let me know if you have questions. Okay, I'm going to try and hammer out the testing center stuff this afternoon, worst case Friday, and I'm going to send you guys an email as soon as I know something. I'm going to try and hammer out the testing center stuff this afternoon, worst case Friday, and I'm going to send